Hello, I am your host, Monique Anderson from Saratech. We are fortunate to have Richard Ozaki here with us today to tell you a little bit about Saratech. For over 15 years, we have been teaming up with our customers to help optimize their processes across their design, analysis, manufacturing, and quality systems. We are an industry leader in the PLM space through our partnership with Siemens, and we are their #1 partner in the Americas. Headquartered in Orange County, California, our team of professionals are located all over the United States to be closer to our customers. Please, if you have any questions or comments, to the right of your screen, enter them in the chat box and we'll respond to them at the end of the webcast. And if also you could please stick around for about 15 seconds to fill out our survey. Let us know how we did and what you liked. We really appreciate it. And now I'd like to hand the reins over to Richard Ozaki.
Thanks very much, Monique. So good morning, good afternoon, everyone. My name is Richard Ozaki. I am an employee of Mentor Graphics, Mentor Graphics was recently acquired by Siemens PLM, so we are now part of the Siemens family. But just a little bit about myself. I am an application engineering technical specialist for Mentor Graphics. I specialize in CFD analysis for fluid flow and heat transfer. I performed my master's degree in turbo machinery, and really my specialization since coming to Mentor Graphics has been in the thermal analysis of electronic systems, so looking at PCBs, components, heat sinks, fans, and that sort of thing. But today we're going to be talking about Flow EFD for automotive. But before that, just a little bit about Mentor Graphics Corporation. As I mentioned, we're part of Siemens PLM now, but we are a software company primarily involved in the EDA software market. So this is software created for the design, automation of PCBs, silicon, cable harness, and we have over 5,700 employees and headquartered out of Portland, Oregon. I myself work for the Mechanical Analysis Division, and we are a subset of Mentor Graphics that develops thermal simulation software and hardware for the market. So CFD technology, CFD stands for Computational Fluid Dynamics, and it's the mathematical prediction of fluid flow and heat transfer. Now this can be applied in many areas of product design. Just a few examples on your screen. So for example, electronic systems, pumps, exhaust systems, external aerodynamics, anywhere where you've really got fluid flow or heat transfer, there are chances are that you can perform a CFD analysis on that geometry. So the product today we're going to be talking about is called Flow EFD, and it is a CAD embedded tool. I just want to talk about a few of the unique selling points of Flow EFD and where it's really very powerful. And the first one is that it's a CAD embedded tool. So we have versions for various CAD systems. I've just highlighted the two Siemens products here, NX and Solid Edge. But because we are embedded within these CAD platforms, there's no exporting of geometry. We are using the CAD directly within NX or Solid Edge, and that's got a lot of benefits, such as not having to export a step file, for example. You don't need to define a fluid region or anything like that, and your design and your CFD models stay in sync, and overall it just gives you a more comprehensive and synchronized overview of the analysis within your CAD system. The second one is the meshing procedure. So Flow EFD uses an immersed boundary meshing technique for meshing solids and fluids. So what this means is that we don't have to worry about polyhedral, tetrahedral meshing elements or anything like this. We have a Cartesian immersed body representation, and what this really means is the benefit for the user is that the meshing, the pain of meshing is really reduced significantly. Right? So you don't need to be a meshing expert to get decent results and generate a decent mesh in Flow EFD. So you can get onto running a lot more iterations and test cases rather than spending all your time trying to get a mesh that will actually solve and converge. The third one is our turbulence modeling. So Flow EFD has a single turbulence model, a K epsilon 2 equation RANS turbulence model. And what this allows the user to do is, over a wide range of Reynolds numbers, you can be confident that the results that you get will be taking into account all of the turbulence wall functions, boundary layers, all of this is taken care of for you without having to select a specific turbulence model or anything like this. And again, we're trying to make it as easy as possible to use, so the user, the CAD user, doesn't have to be a CFD expert to get decent results out of the software. There's various checks and balances within this tool to ensure that you're going to get decent, fast and accurate results. The next one is our treatment of the boundary layer, and this is connected to the way that we handle the mesh. So at the walls, if you think back to your fluids dynamics classes, there's always a boundary layer at the wall, and this is at the wall, that's the geometry that you're modeling. The boundary layer affects the rest of the core flow within your geometry. And if you don't get the boundary layer right, you're not going to get the rest of the simulation, the rest of the core flow right either. So by simulating the boundary layer using an engineering technique, we don't simulate it directly. We use a wall function to do this, and this is combined with our smart cell technology at the wall, so you don't have to have a very fine mesh at the wall. And again, trying to make it as accessible and easy as possible for engineers to get good results. So a focus on no specialization or expertise required to get a good result from Flow EFD. So that's just a little bit of background on the software. Flow EFD can be used in a variety of different applications. We can see the automotive case here today. I'm going to fire up the software in just a moment, but today we're going to be concentrating on 3 different examples. The first one is a water pump, so we're going to be looking at rotational analysis. Then we're going to have a look at an exhaust system, where we can have a look at the flow through an exhaust and looking at the back pressure treatment. And then finally we'll have a look at a quick thermal analysis of a headlight unit as well. So as you can see on the screen, there's various other places where Flow EFD can be used, but I've just picked these 3 just for our brief webinar today. So let's just dive straight into the software and have a look at an automotive water pump. So here we can see an automotive water pump. It's a belt-driven water pump. We have flow that comes in from 4 different inlets over here on this particular inlet. It then passes down through the volute and into the actual impeller. As you can see, there's an impeller which is designed to be span at a certain RPM, and then the flow is then finally going to be, not that one, apologies, the flow is actually finally going to be leaving out of this this part of the geometry over here. So a pump serves to increase the pressure and maintain the flow rate within an automotive cooling system, and if this fails, then your vehicle is going to overheat and not perform. So let's have a look at the actual analysis phase. As you can see, Flow EFD has an extra tab within the NX environment. Now this is NX version 11, the latest version from Siemens, and we have an extra ribbon toolbar component to this flow analysis. So first of all, let's just perform a check geometry analysis, and this will show us where the fluid region in the model is going to be. And this is what I mean about not having to export the geometry. You can just look and verify what the region the water is going to be occupying within the model is without exporting or creating this fluid body part. Okay, so once you've got that, you're actually ready for the analysis stage. So let's just quickly, not that one, go through the Flow EFD wizard to set up some of the base parameters of our project. So I'm just going to choose my unit system and choose my internal analysis. This is an internal analysis, as we know where the flow is coming from and going to. So we can turn on various features in the software. I want to turn on rotation. Okay, so because we actually want to rotate the impeller. Heat conduction in solids, this isn't so important. Radiation, time dependency, gravitational effects. We don't need any of these. We just need the rotation feature turned on for this analysis. And I'm going to choose my default fluid. Now I'm going to run this with 100% water. Okay, so just put water into my project. I can create mixtures of waters, so if I wanted to create, say, a water glycol mix, then I can certainly do that. In fact, I've got ethylene in here, and you can see I can add in a second fluid, and that will take that into account for the working fluid. But for now, we'll just use water. We can also consider cavitation. So if you're concerned that the pressures in your pump are dropping a little bit too low, we can turn on cavitation, and that will ensure that we're solving for any gaseous bubbles or any collapsing bubbles within the flow, which can potentially cause damage to your pump. And then finally, we're just going to specify what our initial conditions are going to be. So this is atmospheric pressure at sea level and temperature at sea level. And that's basically all we need to do for the wizard. And as you can see now, we've actually been presented with a black box around our geometry, and this is what we call our computational domain. So as this has been defined as an internal analysis, right, so we know where the flow is coming from and going to, because it's internal, the software has automatically picked out that fluid region for us, and that's a very, very useful feature for actually determining where the flow volume is going to be. So let's now apply some boundary conditions. So first of all, I'm just going to create a section. Oh, no, it's not there. So let me just turn on a section. Let's create it in the X direction and just flip that around so I can get access to that face. And if we look inside the model, you can see here's the inlet lid. There's the forces air the water onto our impeller. It's span outwards and collected by the volute on the outside. So let's go back to our Flow EFD tab. I'm going to come to Flow Analysis and create a boundary condition. So a boundary condition is a way of introducing mass into a system, somewhere where the flow is going to be entering or leaving. So the first thing we want to do is create a inlet volume flow. So by selecting the internal face of the inlet, I can populate that into our boundary condition dialog box, and then I need to give a volume flow rate. So let's just assume 0.2 meters cubed per minute of water going into our particular pump. And this is going to be a single operating point on our pump curve. And you can see we have these arrows which indicate our inlet flow condition into our pump. Now let's deal with the outlet side of things. And again, I'm going to come back to the view and just edit the section. And let's just flip that over to the other side, again, just so I can get access to this internal face of my outlet lid. And again, let's create another boundary condition. So again, the boundary condition dialog box comes up, and I select the internal face. But this time, rather than a flow opening, we're going to be looking at a pressure opening. So we need to define an outlet pressure. So a typical automotive pressurized water system may be operating at about maybe 2 atmospheres, something like this. So I'm going to come down here to my static pressure conditions and change this to 200,000 pascals, okay, to have my pressurized system. And this time you can kind of see we have these blue arrows which indicate our outlet pressure condition on the model. Just a second while it catches up and recognizes all of these different regions. Okay, and then the next thing we need to do is create a rotating region on the model. Apologies, it's just, I think it's just saving the model as we speak, so just takes a couple of seconds in NX to catch up there. Okay, while it's waiting, I'm just going to hop over to another model while it's doing an autosave there. That's annoying. Is it still doing that? Yes, it is. So the second example that I wanted to show you was an automotive exhaust system. And as you can see, again, we're in NX11. I've already run through the computational, the Flow EFD wizard, and this is going to show us our computational domain. And again, we have an internal analysis. We know where flow is coming from and going to. So we have our computational domain automatically set. You can see that we have a inlet mass flow of exhaust based on the RPM and the displacement of the vehicle. We have an outlet environmental pressure, okay, and from there we can then solve our numerical analysis. Looks like it doesn't like this particular one, so I'm just going to jump over to here. So once we've created all of our boundary conditions in the model, we then need to specify something called an engineering goal. So an engineering goal is a way of telling the solver various parameters and various solution answers that we're interested in knowing about before we actually execute the solver. So for example, I'd like to know what the global mass flow rate through the system is going to be. So if it converges correctly, and it will have 46 kilograms per hour of exhaust gas. We also want to know what the maximum velocity in the model is going to be. We also want to know what the exhaust temperature on the outlet is going to be. And then most importantly, we want to know what the delta P in the whole system is going to be. So what at 46 kilograms per hour of exhaust flow, what's the delta P, what's the back pressure that this particular exhaust system is going to be experiencing? And this will change based on the flow rate through the system, but this is something that we can monitor using FlowEFD, and we can get a good idea of what the flow is going to be. So if I was to run this live, I'm not going to because it takes a little while to actually execute the solver, but we need to generate the mesh. We also need to execute the solver. Now FlowEFD is a parallel processing software by default, so you can run this on as many CPUs as you wish. You can run it on an external machine if you wish, so you can add a network computer and that will do the number crunching for you on an external machine, just so it frees up your desktop for you. And this particular model, well, let's have a quick look. If I go into the summary, it's got about, pretty low, it's only about 60,000 grid cells, and the actual CPU time was less than an hour. So you're looking at about 40 minutes there, roughly, give or take. Okay, and then what sort of results can we get from the software? Well, let's have a look, and if I just go into wireframe mode, this is the computational mesh that has been defined. Let's just spend just a couple of seconds talking about that. So the computational mesh in FlowEFD is Cartesian in nature from the presentation that I showed earlier. The way that it works is it will take these Cartesian grid cells and split those into 4. So as you can see, as we get towards features where we need extra or additional grid, it's increased the grid density for you automatically. As we come over to this section over here, you can see the grid density. It's quite low, but just for demonstration purposes, you can kind of get an idea of what the mesh looks like. And a thing to particularly note is we do not have a fine mesh at the walls. In the boundary layer regions, we do not have that very fine mesh because it's not required in FlowEFD. We have a proprietary method for solving for the boundary layer, which means we don't need that very fine grid resolution. So let's just edit this and have a look at the contours, and let's have a look in the XY plane and turn off there, and let's plot the pressure with 50 gradations, hit OK, and now we can get an idea of what the pressure distribution through our exhaust system is going to be. And this is pretty much what we expected through our exhaust system. So at the inlet end, you've got a higher pressure noted by the higher the red region on the scale, and then on the other end we've got the lower pressure because as the exhaust has to work its way through all these bends and twists and little baffles and little guide holes, the more and more pressure is required to maintain that particular flow rate. So we can probe and have a look at what the pressure in the system is going to be by creating these probe callouts and getting an idea of what the pressure is going to be in the system. We can also have a look at what the velocity is going to look like. So if I have a look at the velocity, right, you can see, as we might expect, most of the flow is going straight down the middle. This one has got very low velocity either side of this box because this one is primarily designed to take the noise energy out of the exhaust system. Okay, but then the second one is used to actually mix it up and break up the flow a little bit, and we can see what sort of velocities that we're going to be achieving in our system by mousing over and showing the various values of the velocity within the model. Another thing we can look at is also turbulence. Okay, so turbulence is an indirect measure of the amount of sound that's being generated in the model. So wherever you've got high turbulence, wherever a flow is forced to increase in speed, you will be able to see where that is in the model, and whenever there's turbulence, that can be associated back to the amount of noise that this particular unit is generating. So we can see where the turbulence is being generated by looking at the turbulent energy within the system. We can also have a look at a surface plot of the pressure within our exhaust system. It's just going to grab the geometry now and we'll have a look at that. Okay, so I've plotted that by velocity still, but let's go back to pressure. And we can see the pressure drop across our exhaust system from the inlet all the way through to the outlet, and that's what our pressure distribution through our back box looks like. And again, we're still in NX, and all the pre and the post processing is done directly within the NX environment. Finally, let's have a look at what the flow dynamically looks like through our exhaust system. We can plot some flow trajectories from the inlet, and this shows us how the flow moves through our exhaust system. So you can see we've got our inlet. This is plotted by pressure. Let's go back to velocity. And now we can see the flow going through our exhaust system. It comes out the end. It's having to swirl around. It's mixing. You've got a little bit of a low velocity region over here. It's mixing together, and then it's coming out towards the back box and then out towards the tailpipe. So you can have a look at what the exhaust is doing within the system, how it's mixing together, what the turbulence looks like, and then try and design your exhaust system appropriately to take into account all of those factors that I just talked about. So that's FlowFD as applied to a exhaust system. Apologies, it looks like my my pump has frozen up on me, so I'm going to jump over to my my headlight unit. So here is a, let me just go solid screen, solid bodies. So here is a motorcycle headlight unit. So this is a classic incandescent lamp unit where we have a bulb with some, it's an H4 bulb with a filament in here, so you can see the geometry, very, very fine features within this fairly large geometry. So large differences in length scales can be observed in this particular model. And FlowFD can be used to perform a heat transfer analysis on this if you wish. So again, flow analysis, you can go through the wizard. We can have a look this time at the computational domain. This is an external analysis. The other two were internal analyses. This one is an external. So you can see the computational domain has been sized with a bit of a buffer zone around the geometry. Okay, we have some fluid subdomains to take into account the fluid region within the xenon bulbs. So we actually have a noble gas in there at a high pressure to stop the filament from burning out. So you can see that's been applied there. And because this is heat transfer, we need to assign materials in the model. So for example, we have tungsten applied onto the filaments of the bulb. We have a quartz glass applied onto the bulb glass. We have a polycarbonate assigned onto the lens faces, and everything else has got an ABS or a polycarbonate material assigned onto it. So most of the construction of this particular unit is made up of a polymer. Now, in terms of the heat source, again, the bulk of the heat is generated by the filament. That's where the electricity is being generated from the battery. So you can see I've set a fixed temperature on this filament. I could just as easily set a power dissipation on this filament as well. So I could dissipate, say, I don't know, maybe 12 watts, 15 watts, something like that on the filament. But for now, I've just used a fixed temperature. I've also defined a diffuse radiation source. So this is a conductive and convective source, and this is a radiative source because obviously there's going to be a lot of heat loss via radiation in incandescent bulbs, so we need to take that into account. And the way that the reflectors have been designed, we'll be able to see how the radiation comes out of that filament, hits the reflectors, and what it looks like as it bounces forwards through the model. So let's have a quick look at some of the results. Let's have a look at the temperature as a cut plot through the model first of all. So we can have an idea of what the temperature around the bulb is going to be. So about 400 degrees C in and around the bulb. If I come and auto range this, you can see that we have this very high temperature around the bulb itself, you know, around the filament. We've got about 2000 degrees C, 1200 degrees C directly above it. And you can see that the air rising against gravity and preferentially heating the top of the bulb. And you can see that by mousing over and probing that plot there. But if I just pull this down to something a little bit more sensible, this will give us an idea of what the airflow within our headlight unit is going to be. This is a sealed unit, so there is no direct air transfer from inside to outside. Okay, and we can get an idea of what the temperature inside the housing is going to look like, and this is with a 50 degrees C ambient temperature. We can have a look at it from the top also to get an idea of what the temperature in the rest of the system is going to look like. Only this one bulb is turned on, the other one is not turned on. We can have a look at that. We can have a look at what the front casing temperature looks like. So as the radiation moves, is reflected forwards, we can see hotspots being generated on our headlight unit. We can get an idea of where those hotspots are going to be, what the magnitude of the temperature of those hotspots are going to be, where the cool regions are going to be as well. So if you've got too much of a delta T across your lens, you might get some warping, which you obviously don't want to do. But hotspots are sometimes good for demisting and removing condensation from inside your unit as well. So there are some benefits to this. If we have a look at the bulbs themselves, you can have an idea of, let's just pull this down to about 500 degrees C, so you can get an idea of what your bulb temperatures are going to get to. And this is typical of an H4 bulb. You will get these sorts of temperatures, and that's why they're kept away from fingers behind all that polymer there, so because they can get very, very hot. And then finally, let's have a look at the housing temperature. So here's the housing temperature. You can see where the hotspot is. So around this mounting hole, this is getting up to a significant temperature, about 100 degrees C. So it could be that due to the way that the air is heated, it's moving up and being forced around here, there is a preferential heat transfer around this and out to the mounting screw. So the software will allow you to get an idea of what the flow in and around your headlight is going to look like and what the temperatures of the final steady state solution is going to look like also. And then let's have a quick look at what the flow looks like inside the unit. Let's just go wireframe. So this is what the flow looks like. If I look at it from the rear, you can see there's a lot of recirculation. Obviously it's a sealed unit, but as the lamp heats up the air, you can see it moves up. It comes over to this hot area over here, and then it has to drop back down due to gravity, and then it's sucked back up and rotated round and around. So this is what the flow looks like inside of our lens unit, inside of our headlight unit, and this will give you an idea of where there are low flow regions, where the low temperature regions are, and this is contributing significantly to the convective heat flow within our headlight unit. So to summarize, why perform CFD analysis in the first place at all? Well, 3 reasons. The first one is reliability. So if your product performs better, if you've performed design iterations and tried different materials and dimensions and combinations of different parts, then it's going to perform better. You're going to have reduced failures, and you're going to have reduced warranty claims and fixes. It's a lot easier to fix parts and assemblies while they're in the design stage rather than once it's been tooled up and in production. You're going to be seeing reduced design costs also. So by reducing the design, build, test and fix cycle, we're reducing prototyping costs. So the actual physical costs associated with manufacturing prototypes is reduced. And then also we're going to be reducing the design time. So you know, if you're spending less time testing and prototyping, then you're going to have reduced lab costs, you're going to be faster to market. So right here is really what the ROI of performing a fluid flow and heat transfer analysis with CFD is giving you as engineers to make better design decisions on. So this has been a 30-minute overview of Flow EFD for a couple of different automotive applications. Again, apologies about the pump model, but if you do have any questions about any specific applications, automotive applications, or anything specific about Flow EFD, please feel free to type them into the chat box. And Monique, do we have any questions, please?
Yes, Richard, that was a great presentation. We have a couple questions in. Our first question asks, can Flow EFD model cavitation in pumps?
Yes, it can. Yes, so I kind of touched on that a little bit earlier, but we can do cavitation. So if the local pressure, the local water pressure in your system drops below the vapor pressure, then you can actually start drawing air bubbles out of the flow, typically where the flow is going the fastest. It can be applied for things like pumps, but also things like propellers in ships. Those can cavitate. Fuel injectors can cavitate. Whenever you've got very high velocity flows, you could be seeing cavitation, and FlowEFD can model that.
Okay, great. Second question says, what radiation models are available for automotive lighting?
Okay, yes, so sure. So FlowEFD's got a few different radiation models. So if I come over to the general settings, so we have 3 different models. So we have discrete transfer, discrete ordinates, and Monte Carlo, and it really depends what sort of analysis that you're doing. In this example, I'm using Monte Carlo, which is a statistical method. Because I'm lensing the radiation, because I'm forcing it through a semi-transparent solid, such as polycarbonate or PMMA, I want to see that absorption in the solid. So few different radiation models based on what you want to simulate. So we got standard ray tracing, view factors, or we got the Monte Carlo statistical method.
Perfect. And then one last question, can FlowEFD predict sound or acoustic performance?
It's kind of touched on that very briefly. We can't predict the acoustic performance in decibels, but we can have a look at the amount of turbulence that's being generated within a system. So you can get an idea of a magnitude of the sound. So you can compare 2 different models. If the turbulence is less in one of the models, then you can be pretty confident that it's generating less sound. You're forcing more of the energy of the flow out the end of the exhaust rather than it dissipating within the model. So yes, we can predict sound, but not directly.
Okay, great. Well, those are all the questions that I saw for now. We did get one question in regarding will slides be made available, so this goes to that person. We will be posting this video to YouTube later today, so please feel free to pass along to your friends and colleagues, and please be sure to subscribe to our channel. Follow us on Twitter and LinkedIn for upcoming webinar dates and topics. And please, if you could just stick around for 10 to 15 seconds to fill out the survey, let us know how we did and what you liked. We really do appreciate your feedback. And thank you everyone so much for attending. Great presentation today, Richard, and hope everyone has a great day.
Yeah, just to add on the end, if you are interested in learning more about FlowEFD, or if you'd like a bit more of a custom presentation, or someone from Saratech to contact you about that, feel free to contact any of these links on the screen, and someone will get back to you very shortly.
Perfect. Great. Well, thank you everyone. Have a good day.
Thank you. Goodbye.